to the Chatham Marconi Speaker Series. My name is Liz McCart and I'm a volunteer here at Chatham Marconi. We are so pleased that you have joined us tonight for the program and appreciate your support. At the museum, we are often asked, what did Marconi do next after RCA purchased his American company? Did he go on to build another company or continue to build something in Britain? So tonight, we are so pleased that we are joined by our speaker, Paul Hawkins, who is broadcasting from the United Kingdom. So it's a bit late there, but he's going to be telling us about what Marconi did next in Britain and beyond, as well as talk about international communications from Marconi's era through current. So it's my privilege tonight to introduce Paul. As a reminder, if you have a question during the broadcast, you can hover your mouse over the bottom of your screen and you'll see the Q&A icon. Type your question in during the broadcast and you'll have some time after Paul's talk to ask questions, and we'll get to as many as possible. So Paul Hawkins enjoyed a 40-year career in radio communications. He joined the British Post Office International Telecommunications Service in 1967, working at the Dorchester High Frequency Transmitting Station, the Gonhilly Satellite Station, and the Barely High Frequency Receiving Station. From 1980 to 1983, he worked as a radio frequency design engineer for a defense firm in Massachusetts. Between 1983 and 2013, Paul worked for the Thales Company in England, where he led the design of antennas and communication systems for submarines, ships, and land mobile vehicles. Paul retired from full-time employment in 2014, but that doesn't mean he hasn't been busy. Radio and its history are a personal interest of his, and he's published a number of articles. His book, Point to Point, A History of International Radio Telecommunications, was first published in December 2017. He's given lectures to multiple organizations, most notable being that at the Institution of Electrical Engineers at their 100-year wireless conference in London. In 2015, he gave a lecture on the subject of Marconi beam wireless stations at a conference in Bologna, Italy, where he met Princess Elettra Marconi, the daughter of Marconi, whom we've also had visit our site here. Paul is also a licensed ham, and his call sign is G4KHU. So with that, Paul, I'm so happy and pleased that you have joined us tonight. And thank you for staying up so late to talk about the history of communications. And I'll turn this program over to you.
Very good evening to you. Very good evening to everyone. And thank you, Liz, for that introduction. My name is Paul Hawkins, yes, and I'm going to talk to you about telecommunications, a time not so long ago when mobile phones didn't exist. Sometimes telephones didn't even have a dial or push buttons, and a text message was a telegram. In the 1970s, Liz has given you a good introduction. I was a technician at operating some of the last remaining international telephone and telegraph circuits that were carried by HF or shortwave radio. Yes, I started my career in 1967 at the British Post Office transmitting station, pictured behind me in actual fact. So it gives you some idea, which was was indeed a Marconi beam wireless station. My passion for radio really developed when I moved to a receiving station, because there, listening to the radio waves and the signals coming in, you get a real good feel for shortwave radio and all its quirks. However, at that time, with the impact of satellite communications, there wasn't an awful lot of interest. Shortwave radio was going out of fashion. So when I tried to investigate the history of radio service, most of the books I read seemed to make a graceful leap from Marconi's 1901 achievement across the Atlantic, and then just took a leap to the launch of Telstar in 1962. And what happened in the 61 odd years between just seemed to be glossed over or mixed up with radio broadcasting or just completely forgotten. However, I think a great deal was invested in radio technology and electronic technology during those forgotten years. And when I say a great deal invested, I don't just mean the money invested by RCA and Bell in the USA and Marconi and the British Post Office over here, but also by scientists and engineers who put an awful lot of time in trying to refine the service. So anyway, as the title suggests, I'm pleased to provide a short historical perspective on what Marconi did next and beyond in the field of international radio telecommunications. So we move to the next slide. Here we see two of the stations that Marconi was responsible for. At the top, Poldhu in Cornwall, which is where the research and some initial operations were conducted, and below the Marconi station at South Wellfleet, Massachusetts, one of a number of locations that Marconi established in North America. In 1901, the transmitter technology was somewhat crude, ranging from sparks, continuous wave arcs, and of course all operations were concentrated in the long wave LF and VLF bands. After Marconi's pioneering transatlantic venture in 1901, it was several years before a regular, reliable transatlantic telegraphy service was established, and using powerful arc transmitters and tube receivers enabled the company to compete with the established cable systems. The first sinusoidal continuous waves were generated by Reginald Fessenden, a Canadian working in the USA, with the use of the high-frequency alternator. This seems to have been the first time that the words high frequency was used, although the highest carrier frequency was produced was around 100 kilohertz, still in the long wave band, and it was keyed by varying the current in the field windings. Pictured here is the ultimate development of Fessenden's transmitter, the 200 kilowatt alternator developed by Dr. Ernst Alexanderson, shown here at the Marconi station near Carnarvon in North Wales and at Marion, Massachusetts. These alternators were also installed at Rocky Point and other locations in the USA. Fortunately, one of these transmitters, one of these alternators has been preserved in operating condition in Sweden, and it comes on the air from time to time. And for those unable to receive SAQ, I've just got a little sound clip here. The limitations on radio communications may have been the electrical nature of the equipment, but an incomplete understanding of radio propagation in those early years also indicated that the radio spectrum was unreliable or virtually useless above 3 megahertz. So for a short period of time, radio hams had free reign of the shortwave spectrum. The first tubes were invented by Fleming and DeForest and were rather delicate items used for low frequency amplifiers and signal detection. But as this new device became better understood, its performance and reliability improved, notably with the use of a high vacuum. The first radio frequency oscillators using tubes were invented in 1913 by Alexander Meissner of the Telefunken Company in Germany, quickly followed by Franklin and Round of the Marconi Company. This was the first step towards electronic transmitters. In the USA, Westinghouse built a tube transmitter in 1915 that achieved a transatlantic link. And by 1919, transmitting tubes rated at several kilowatts were in mass production. And in 1920, the Marconi Company assembled this 100 kilowatt transmitter shown here in using what they call a panel of 54 tubes at the Carnarvon station in Wales, all very open and high volts. They're ready for anybody to, electrocute themselves, and they weren't careful. But anyway, moving on. In the UK, the Marconi built additional transmission, long wave transmitting receiving stations just 20 miles from London, near the Marconi factory at Chelmsford in Essex. These were the first generation of electronic transmitters and receivers using tube technology. And in 1922, their purpose was for communications with several European countries, although these stations also operated some wireless telegraph traffic to North America. Around the same time in the US, operations at Rocky Point and Riverhead were also commencing, and Chatham and Marion then became more focused on maritime communications. By then, Marconi's US operations had been taken over by RCA. Now, in 1924, the receiving station at Brentwood, shown here, and not to be confused with a radio station at Brentwood, Long Island, became the main long-wave receiving station in the UK, receiving wireless telegraph from Glace Bay in Canada, Rocky Point, Marion, Tuckerton, and New Brunswick in New Jersey. However, Marconi was not the only one making advances in wireless telegraphy. The British Post Office had a bit of an on-off relationship with Marconi and were actively engaged in developing their own transmitter technology. This was done very successfully with the 16 kilohertz long wave, or very long wave transmitter at Rugby, call sign GBR. This was capable of delivering 500 kilowatts into a large antenna hung from 820-foot masts, providing worldwide coverage. In 1926, when Rugby commenced operation, it was claimed to be the most powerful all-tube transmitter, and this was when most powerful transmitters around the world were still using the old electrical technology. But long-wave wireless had just about reached its zenith. The discovery of shortwaves. Long-wave radio had many limitations, and the time had come for radio communications to break out of long waves and sparks. As early as 1915, Marconi had been concerned that long-distance wireless was getting into a rut of longer waves and higher power. Frustrated by these limitations, Marconi directed research into much higher frequencies. And this work was conducted by Charles Franklin, pictured here, who investigated shortwaves and also VHF. Numerous tests were conducted between Poldhu and Marconi's steam yacht Elettra, establishing some of the basic characteristics of shortwave propagation. This led to a conclusion that reliable daytime shortwave communications could be achieved between the UK and South America. I would say that some credit should also be given to amateur experimenters whose tireless work pushing the known boundaries of the science are often an inspiration to the professionals. In 1924, the Marconi Company won a contract from the British Post Office for the shortwave beam system to communicate with Canada, India, South Africa, and Australia, which at that time were the major countries of the British Empire. There were a number of challenging requirements to meet, such as an average of 100 words per minute over the agreed daily schedule. Charles Franklin became the technological architect of the shortwave beam system. He had responsibility for the development of a 20 kilowatt transmitter, the antenna system, and the means of conveying the RF power from the transmitter to the antenna. The transmitter, pictured here, was called the SWB1, the Shortwave Beam 1. And there are four so-called panels, one of which is the power amplifier. Two of the panels are the exciters, one for each of the two frequencies used in the daily schedule. And the fourth panel was for power supplies and transmitter keying. It can be seen here how transmitter designers already progressed from the panel of valves in the earlier picture to the slightly more conventional layout, albeit with minimal safety constraints. Beam antennas were a notable piece of engineering. And while electronics has changed beyond recognition, antenna theory remains much the same. Franklin developed a uniformly excited broadside phased array. It's a bit of a mouthful, but that's what it was. The antenna, which became known as the Franklin beam, used a number of collinear vertical radiating wires with a screen of vertical wires placed behind to form a reflector. The number of radiating wires varied between 8 and 24, depending on the frequency. For most services where two frequencies were required for day and night operation, two antenna arrays are required, and a typical beam antenna system was suspended between 5 masts, spaced at 650 feet. The masts were 280 feet high. So a whole beam array was half a mile long. And this picture shows the 5 masts on the left of your picture is the beam array directed on North America. And then the picture also shows 2 smaller arrays, that one was used for South America and the one further away behind was used for Japan. The beam pattern, the picture in the top left shows the efforts made in plotting a beam pattern, and there's a graph of the actual beam pattern. So it shows it's a very narrow beam. This slide shows the HF receivers designed for the beam system by the Marconi engineer G.A. Matthew. 2 shortwave receivers are mounted on a frame, and the receiver was a tunable superhet with the majority of amplification in a low frequency IF stage, where the higher gain could be extracted from the tube amplifiers. The IF bandwidth was relatively wide to allow for drift of both the transmitter and the receiver, and this was a time when local oscillators were LC tuned and not crystal controlled. The receiver was required to provide reception of high-speed Morse, and the output data was printed on paper tape, known as slip, or I'm not sure, or ticker tape, I'm not sure what you call it in America. And the audio output was provided for operators to tune the radio. For the British Post Office owned Empire radio system, as it became named, there were transmitters in the UK at Bodmin and Grimsby, and receivers at Bridgewater and Skegness. These were the first ever purpose-built shortwave stations. The first service commenced operation between the UK and Canada in October 1926, and from that point on, shortwave radio became the backbone of long-distance communications. The transmitting and receiving stations owned and operated by the Marconi company were also built at Dorchester and Somerton, southwest of England. They commenced wireless telegraph services in 1928 to the USA and other non-empire countries, including Brazil, Argentina, Egypt, Japan, and China. Marconi had taken the world by surprise with the development of shortwaves. However, his competitors were fast learners, and shortwave systems were soon being produced in America and in Europe. The large spectrum now available compared to that at the low frequency bands combined with the new technology of radio broadcasting, soon offered the possibility of intercontinental radio telephone. The HF spectrum soon started filling up, and radio hams had their rights confined to the well-known harmonic bands. From around 1930, the Marconi stations in the UK were taken over by Cable and Wireless Company. It was a change influenced by politics, something we don't have time to discuss here, but in the UK, Marconi became just a manufacturer of equipment. Now, although, as I said, telegrams could be sent worldwide via radio and undersea cables, long-distance telephone was limited to the near continent. The first intercontinental radio telephone service was, not surprisingly, between New York and London. It was developed over a period of 5 years by AT&T / Bell Labs and the British Post Office. And this was done before there was full knowledge of shortwaves. Hence, it operated in the low frequency band at 60 kilohertz using single sideband modulation. In the US, the transmitter was located at Rocky Point and the receiver at Halton in Maine. In the UK, the transmitter was at Rugby and the receiver was at Coupar in Scotland. The service opened to the public in January 1927 and calls cost $60, yes, $60 for a 3-minute call. Fortune at that time. Along with the radio frequency aspects of international telephony, new technology had to be developed to deal with baseband signals. This included the interface between the telephone system and the radio system, plus the invention of echo suppressors and constant volume amplifiers to maintain transmitter drive levels. With the opening up of shortwaves for telegraphy, the development of transmitters capable of amplitude modulated telephony soon followed. Between 1928 and 1930, three new channels opened up on the New York to London service, and the price of a 3-minute call was reduced to $30. Services between New York and many other capitals soon opened up as the world became crisscrossed by radio telephone links. This picture shows the Australian telephony transmitter at Rugby, sometime after it commenced operation in 1930. You can see there's a huge number of control knobs, and I often say nearly as many as on my Obiasu FT1 radio. But anyway, by the mid-1930s, the next generation of HF transmitters were certainly safe for being fully enclosed. The ones shown here are the Marconi SWB8/10 transmitters, and the SW8, which is the box in the middle, I guess, was a 3.5 kilowatt transmitter, and then the SWB10 was a 25 kilowatt power amplifier. And these were primarily used for telegraphy, radio facsimile, and some AM voice. Improved master oscillators with crystal control and improved power amplifier linearity gave some transmitters the stability to operate single sideband telephony, and 2-channel independent sideband operation followed shortly afterwards. Oh dear, I apologize. Returning to antenna technology, most of the shortwave antenna systems that have been developed were on similar principles to the Franklin beams, these being large tuned arrays designed by Bruce, Sturber, Walmsley, all sorts of people. And these antennas were limited to single frequency operation, and so were a significant expense in the development, in the operation of a global radio network. A breakthrough came in 1931 with the inverted V antenna designed at Bell Labs by Edmund Bruce. Initially operated as a tuned antenna, but when combined with some features of the long wire wave antenna, it soon developed into the Rhombic, capable of broadband operation and considerably more economic in terms of installation and maintenance. Although not possessing the gain of a single frequency beam antenna, the Rhombic was a good compromise between cost and complexity. And with the higher output power available from tubes at that time, the gain lost in the antenna could be added in the transmitter. This picture shows a nested multi-wire Rhombic antennas, fairly typical implementation in later years. The multi-wire helps to stabilize the impedance, and the nested pair of antennas enables optimum selection for frequencies above and below 10 megahertz. This is a bit more complicated. The main problem with shortwave operation was fading of weak signals. Fading occurs when the ionosphere spreads a signal into two or more paths, which are then received at different times or phases. One solution was to use diversity reception, where two Rhombic antennas were spaced sufficiently far apart to avoid simultaneous fading in both antennas, and thus improving the reliability of circuits. However, this didn't always work. And in 1935, in an effort to reduce these effects on radio telephone circuits, Bell Laboratories commenced designing a multiple unit steerable array, the Musa. And the Musa antenna employed a phased array, initially of 6 Rhombic antennas, and then later increased to 16, together with a very sophisticated receiver, which provided a narrow, steerable beam in the vertical pattern that could discriminate between multiple incoming waves to defeat multipath fading and distortion. The Musa receiver had 16 channels, one for each antenna, the output of which was combined through phase delay networks to provide an electrical steerable array with very high directivity. Assuming a Rhombic had 15 to 18 dBs of gain, the Musa with 16 antennas added another 12 dBs with a very sharp beam pattern. In the UK, the Post Office Research Centre produced a receiver closely based on the Bell Labs design, and a Musa receiver station was set up 30 miles east of London. The system was the ultimate in HF reception and provided a significant improvement in circuit availability and quality of the telephone service. The receiver was perhaps the most complicated HF radio ever built, employing around 1,000 tubes, and was therefore very expensive. Hence, it was only economic on heavily loaded trunk routes, such as New York to London. Given the period in use of tubes, I think the whole antenna system and receiving system was a really astonishing piece of engineering. Now then, this rather colourful map was produced by the British Post Office in 1937 to celebrate 10 years of international radio telephone. It shows the various routes, plus diagrams you can see around there under the sun, and around on the other side, radio propagation and pictures of the telephone exchange and the transmitter in these small insets. By 1937, radio telephone had spread rapidly from the original New York to London long-wave circuit, and there were now around 100 HF radio telephone links across the world, making it possible to interconnect 93% of the world's telephones. New York to London was now up to 6 channels. Another side to all this was regulation of the spectrum, which started almost as soon as wireless telegraph began. There were various international conventions and agreements to manage the spectrum, allocating bandwidth to point, maritime, broadcasting, the military, air traffic control, and ham radio. Now, we think of work at a radio station as technicians servicing and tuning transmitters and receivers, but we shouldn't forget that there was a virtual army of workers doing all sorts of other jobs. As the pictures show, motors and generators and cooling pumps had to be serviced, and even the main power generators, which at some of the stations in the UK had to generate their own power until there was a publicly available power supply. And perhaps the worst job of all was painting the beam masts. being winched all the way 280 foot to the top of a mast, being winched up on a rudimentary platform, as you can see, with there was no stainless steel or galvanized metal here. And as you can see, at a time, personal protection and safety harnesses were unheard of, and the workforce was, of course, exclusively male. Now, during World War II, there was a huge increase in traffic, and additional transmitters and antennas were installed. All radio telephone services were suspended, with the exception of a reduced number of transatlantic channels. Using the long wave or the shortwave radio telephone channels, President Roosevelt was able to call Winston Churchill at any time of the day or night, and they did. Some stations, like the one shown here at Dorchester, were covered in camouflage netting in an attempt to hide the buildings from enemy bombers. In fact, a couple of bombs were dropped near the station, but luckily missed their target. And I think the blast just broke a few windows. But during the winter of 1941, snowfall wrecked much of the camouflage. And across the country, a lot of damage was done with antenna wires and telephone wires breaking under the weight of ice, and more stress in an already difficult period when bombing was taking its toll on everywhere, including the telecoms infrastructure. In addition to their normal duties, workers at radio stations formed Home Guard reservist units and performed guard duties after their normal working hours. Here we see the Home Guard unit from Dorchester radio station. Many of the younger men joining the forces, there was a shortage of manpower, so women were recruited and hastily trained to conduct radio operations, particularly at receiving stations like Brentwood, shown here. In another effort to mitigate the shortage of manpower, the first steps were taken to provide remote control of transmitters, which allowed them to be located in unmanned outstations. These transmitters were pre-tuned to the operating frequency, but were switched on and off remotely with control circuits operating the power to the filaments, the HT, and the ancillaries in the correct sequence. After 1945, there was a huge growth in international radio, telephone, and telegraph traffic, not least to the damage to the telecoms infrastructure across Europe. Throughout the 1950s, there was a significant investment by the British Post Office at several of its radio stations, with new 30 kilowatt transmitters installed by ST&C, which I believe was an ITT company, and the Marconi company. This new generation of transmitters embodied the latest remote control technology and could be preset to a number of crystal control frequencies. Tuning was achieved using servo mechanisms, and frequency changes were controlled from a remote control console. The appearance of the transmitter, as you can see, took on a more modern appearance, with everything hidden behind plain cabinet doors protected by safety interlocks. These developments increased the service availability and required less manpower. This picture shows typical communication receivers installed in the 1950s. The technology at this point is still 100% tuned. The receivers were manually operated, and they employed a tuned front end, VFO or crystal controlled local oscillator, and had a first IF of around 3 megahertz. Automatic frequency control was achieved using a frequency discriminator, which drove a small tuning motor to maintain a lock on the selected transmission. Dual front ends were also included for diversity reception, with the best signal path being automatically selected. These receivers were still in service in the 1970s during my time in the business, and I enjoyed operating them. In the early 1960s, the transistor began to influence new equipment design. The Plessey Company in the UK produced a 100% semiconductor receiver for the British Post Office to re-equip its receiving station near Stratford-upon-Avon. The receiver design changed radically from the old scheme of RF stages with a low IF to the modern scheme of broadband front ends, bandpass filters, and a first IF above 30 megs. Phase lock loop controlled synthesizers became an integral part of the receiver design, as did remote control. For technicians maintaining these receivers, this was more of a challenge due to their complexity. Moving from the tube-based receivers they had been used to, these new receivers are probably like asking a mechanic who maintained a 50s Chevy to work on a Formula One car. And add to that the problems that often occur with first generations of new technology. These new receivers were operated remotely from the control room shown here. I spent many happy hours in this room. The desks had Plessey 155 receivers, and which were used for checking signals and that sort of thing, and also very useful for listening around the amateur bands. It was right here, during the quiet periods on the evening shift, the guy I worked with was ex-Army Signals, and he would give me Morse code practice. Just as receivers had become synthesized, the same technology was applied to transmitters. Fully automatic tuning was successfully incorporated in these 30 kilowatt transmitters from the STC QT range, shown here at the Ongar radio station in Essex. Along with antenna selection, all remotely controlled. Not quite so interesting to look at, but developments in baseband and terminal equipment also improved the quality of HF communications. For telegraphy, the quality and throughput improved with the changeover from high-speed Morse to teleprinter systems, and then this was followed by the introduction of error detection and correction systems, ARQ, which permitted radio telegraph systems to be connected to the automatic telex network. Additional capacity was gained with the introduction of multi-channel FDMX, frequency division multiplex telegraph systems that could transmit 6 or 12 teleprinter channels within a single 3 kilohertz speech channel. For telephony, excuse me, amplitude compression of speech improved the transmitter loading and intelligibility at the receiver. The development of this principle resulted in another advance in radio telephone speech quality. The constant net loss terminal equipment was a system of compressing amplitude of speech before transmission and expanding it after reception. The compression and expansion was linked by a frequency modulated control tone transmitted over the radio link, opening and closing the radio channel at the syllabic rate of the speech being transmitted. This made the channel less susceptible to noise and interference, and the compressed speech enabled the transmitter to operate at a higher average power level. It was first used in 1965 on the New York to Buenos Aires service and the London to New Delhi service, and soon became established on the majority of HF radio telephone channels. But these were some of the last developments in the technology of HF radio. We're now reaching the time that satellites and amplified cables were starting to take the lion's share of international traffic. However, for smaller users of international telecoms, HF radio was still the most economic approach, and hence investment in new HF systems continued for a while. In terms of traffic and coverage, HF radio telecommunications reached a peak in the 1950s, with demand remaining fairly constant until around 1970, when it was gradually superseded by cable and satellite. The New York to London telephone service was operating 14 channels before it transferred to cable in 1956, whilst the number of wireless telegraph channels continued until around 1962. I'd just like to hear a few short examples of what HF telecom circuits sounded like. And the first one, there we go. The first one is a 96 baud, which is 2 teleprinter channels, basically. So that was 2 channels. And then this one here is the frequency division multiplex, one with 12 channels. Next comes the identification recordings. These were used during circuit lineup of HF radio circuits of telephone service at the beginning of a daily schedule. So the first one we got here is New York.
Circuit adjustment packages from a radio station of the American Telephone and Telegraph Company. This station is located near New York City.
This is the London reply.
This is a transmission from the London terminal of the British Post Office point-to-point radio telephone network. This announcement is for station identification and receiver adjustment only.
And then there's one of the transatlantic liners, the QE2, which operated effectively as an overseas terminal.
This is a test transmission from IMS Queen Elizabeth II, Golf Bravo Tango Tango. This transmission is for station identification and receiver adjustment only.
Now we go on to the next slide. Much of this presentation, like me, comes from a British perspective. However, in my research, it was hard to miss the extensive network of wireless telegraph services operated by RCA and the radio telephone services operated by AT&T. This map shows the extent of the RCA network operated from New York, using transmitters at Rocky Point and receivers at Riverhead. RCA obviously operated services to Asia and the Pacific region from San Francisco and Honolulu. Then on the next slide, this map shows the extent of the radio telephone network operated by AT&T from New York in the mid-60s, and transmitters at Lawrenceville and receivers at Netcong in New Jersey. AT&T also operated service to the Pacific region from Oakland into the Caribbean from Miami. With every European capital wanting direct links to the USA, RCA and AT&T stations serving New York would have been very, very busy. A typical international service to a smaller country in the late 1960s would have been 2 phone channels on the upper sideband and a multi-channel telex system on the lower sideband, 1 transmitter with about 12 kilohertz of bandwidth. So now we're moving to slightly to the present, or near the present anyway. Here we see what put HF radio out of business. This is Goonhilly, just a few miles from Marconi's original station at Poldhu, and one of the first fully operational satellite stations. For customers, satellite provided better quality, more bandwidth, more channels, and also TV and video. Over the period between 1965 and 1980, virtually all HF international traffic migrated to satellite. Of course, everything I've spoken about here today was during the days of analog electronic systems. And since then, the digital revolution and fiber optic cables have seen the satellite stations that put HF radio out of business themselves put out of business. And oh, by the way, I had a bit more hair then as well. I've included this slide to show how far we've come in 100 years. The digital revolution, coupled with fiber optic cables crisscrossing the oceans of the globe, has revolutionized telecommunications. Satellites, in the main, do not come close to providing sufficient bandwidth in this digital age, and those that remain provide long-distance mobile maritime communications newsfeed and news feeds from new correspondents. Although, of course, Elon Musk and his Starlink constellation may attempt to buck this trend. But if we think that the first transatlantic wireless telegraph links were aimed to achieve 100 words per minute, and we're now a century later or so, and the transatlantic fiber optic cables are providing something approaching 100 terabits per second. Long wave and shortwave radio utilize the bottom 30 megahertz of the spectrum, shared between all users. But with a digital fiber optic cable, we can hope to get 30 megs of personal bandwidth each if we're lucky. We've certainly come a long way beyond the work of Marconi and the other innovators in the field of radio communications. Well, I hope this talk was reasonably interesting for you. I think we have time for a few questions, but before we do, here's a short commercial break. If you've enjoyed my presentation and would like to know a little more about radio telecoms, you may be interested in the book I have published on the subject, titled Point to Point, A History of International Telecommunications During the Radio Years. And if anyone would like to speak to me in more detail about anything, any subject, you're welcome to contact me via email. Thank you very much for your attention.
Thank you so much, Paul. That was an amazing journey of wireless communication over a very long period of time. And I've read your book, and it's very good. It's very detailed. And so those that are interested, it is a great read from a global perspective. So we do have time now for some questions. As a reminder, just type them in the Q&A box at the bottom of the screen, and we will have Paul answer as many as we can get to. We already have one question. It is about Marconi, so we're going to go back to that topic for a moment. I think you mentioned that Marconi, he stopped development, but he went into manufacturing of equipment. Is that correct? And why was that?
Yeah, in the following the success of the shortwave beam system, a significant number of the worldwide cable telegraph systems were privately owned and were British owned by British companies. And following the success of the shortwave beam systems, the traffic on the cables all diverted to radio. And these cable companies, who've been established since the 1850s, something like that, were just about to go out of business. However, they were well established and well connected, and they were able to persuade the government, and probably rightly so, that there were benefits to have cable and radio and not competing against one another. So the government sort of engineered a takeover, or a combination or a merging of the wireless and cable services, and that created this new company called Cable and Wireless, which was a private company, although the government had a lot of shares in it, and so all the Marconi services, the radio stations in the UK, were all transferred to the new Cable and Wireless company. Just as the cable companies, their assets were also transferred into it. So at first it was called International Communications, something like that anyway, International and Imperial Communications, and then it became Cable and Wireless Limited in the end. So that's what happened in the UK. Now elsewhere in the world, Marconi continued to operate some of his stations, but that's what happened. So in the UK, Marconi became just a manufacturer and developer of electronic equipment. I would say though that even under Cable and Wireless tended to purchase Marconi equipment, and a lot. It was installed all over the world, in actual fact. So I hope that helps to answer the question. It's a bit like actually RCA. The American government not being happy about Marconi owning communication assets and wanting an American company So the RCA takeover, you know, the same sort of thing, really.
Right, thank you. And just a little follow-up to that. How long did the Marconi company of Britain continue to manufacture equipment?
Well, of course, it was subject to further mergers and acquisitions, but the Marconi name was still in existence probably into the 1990s. And then it became merged. There were a number of mergers and acquisitions, and it ended up as part of BAE Systems. But the Marconi factory at Chelmsford continued, and the research facility near Chelmsford, Great Baddow, continued for a number of years. So until relatively recent times, anyway.
Thank you. So at this point, is the Marconi company out of existence?
I think pretty much it is, yeah, because it's been dissipated basically. You know, there's no, difficult to trace. I'm not necessarily qualified to answer that question, because I've been out of the loop for a few years now in the manufacturing and that sort of thing. But yeah, as far as I know, I don't think you'll find the Marconi brand on anything nowadays.
Okay, thank you, Paul. And we have another question from a guest viewer. Were all the towers built on public property?
It's not a bad question, actually. No, by and large, Marconi purchased the land, or attempted to purchase the land that he built the stations on. In the UK, I can't speak for elsewhere in the world, but generally speaking, that he purchased the land, or sometimes leased it. Obviously, it's to do with how land ownership works. Yeah, that I think I'll keep a simple answer. It can be more complicated than that, but yeah, it was leased, and then they arranged lease. So they bought the land probably from farmers and people like that, and then leased the land for farming use back to the same farmers they bought the land off to put the radio stations on. You know.
Okay. Yeah. Okay. Thank you for that answer. Another question or observation is just about fiber optic cable. I mean, cable's been used a long time, and so is it the most prevalent use of global communication today, or it sounds like satellites are not being used as much as they were?
I think satellites currently carry about 0.5% of international traffic, because the fiber optic cables have got such huge bandwidth. I mean, we wouldn't be having this conversation if we were relying on satellite links. Well, I guess we could be doing it, but by and large, with all the traffic on the internet, you imagine, all the Zoom contacts and all the other stuff that's flowing backwards and forth on the internet all goes by a fiber optic cable.
Okay, thank you. And I know it's getting very late in England at this point, Paul, so we probably should wrap things up. And I do want to thank you again for participating with us and for such an informative talk. In appreciation of your time and effort, we are going to send you a Chatham Marconi Maritime hat, as well as a membership to the Chatham Marconi Maritime Center. So you'll have to cross the pond and come visit us
Thank you.
as a member.
Thank you very much. I appreciate that.
You're welcome. And I'd also like to thank our viewers tonight for participating in this program and for your support and however you support us, whether it's volunteering, membership, donations, being part of this viewing audience. So thank you very much. And stay tuned for our December speaker, who will be Bill Giroux, an author who's written 2 books on the World War II convoys. And he's going to join us to talk about those amazing set of events that took place in World War II. Thank you again. Thank you again, Paul. And we'll see you next month. Good night.
Thank you very much. It's a pleasure.